Welcome to this question on thermodynamics, where we're going to look at converting from degrees Celsius to degrees Kelvin, the amount of energy required to raise the temperature of a sword from 19 degrees Celsius to a forging temperature of 998 degrees Celsius, and if that sword was then dunked into a bucket of water to cool it down, how to find the equilibrium temperature of the water and the sword. A 1.35 kilogram carbon steel sword is being forged at 998 degrees Celsius. The specific heat capacity of carbon steel is 490 joules per kilogram Kelvin. The sword is then dunked into a 19-liter bucket of water at 21 degrees Celsius. The specific heat capacity of water is 4,182 joules per kilogram Kelvin. In part A, we're going to find the temperature of the water in Kelvin. In part B, if the carbon steel was originally at 19 degrees Celsius, we're going to find out how much energy was added to get it to 998 degrees Celsius. And in part C, assuming none of the water vaporizes when the sword is dunked in the water, we're going to find what would be the final equilibrium temperature of the water and the sword after cooling the sword in the water bath. We start by solving part A. What is the temperature of the water in Kelvin? To convert a temperature from Celsius to Kelvin, we need to add 273.15 degrees. So temperature in degrees Celsius plus 273.15 equals the temperature in degrees Kelvin. And now we can substitute our value in Celsius to get our value in Kelvin. So 21.0 plus 273.15 equals our temperature in degrees Kelvin. 21 plus 273.15 equals 294 degrees Kelvin, and that's our temperature in Kelvin. Conversely, if you want to switch from a temperature in Kelvin to a temperature in Celsius, we put our value for the temperature in Kelvin here, and we subtract 273.15 to get our value in degrees Celsius. So what is the temperature of the 21 degrees Celsius water in Kelvin? It's 294 Kelvin. And now we're ready for part B. In part B, we're asked if the carbon steel was originally at 19 degrees Celsius, how much heat energy was added to get it to 998 degrees Celsius? All of this energy is utilized to increase the temperature of the carbon steel. It doesn't undergo a phase change because carbon steel melts at extremely high temperatures, around 1400 degrees Celsius. So because all we're doing is heating up the carbon steel, we use our equation Q is equal to mc delta T. So Q, or the heat added, is equal to the mass of the carbon steel multiplied by C, the specific heat capacity of the carbon steel, and multiplied by the change in temperature of the carbon steel. Delta T is equal to the change in temperature, so temperature final minus temperature initial. So we can rewrite this as Q is equal to mc temperature final subtract temperature initial. Substituting our values into this equation, we get Q is equal to the mass of the sword, which is 1.35 kilograms, multiplied by the specific heat capacity of carbon steel, which is 490 joules per kilogram Kelvin, and multiplied by our temperature final, which is 998 degrees Celsius, 998 degrees Celsius, subtract our temperature initial, which is 19 degrees Celsius. 998 degrees Celsius minus 19 degrees Celsius gives 979 degrees Celsius, and this is still multiplied by the specific heat capacity of carbon steel and our mass of our sword is equal to Q. Multiplying 1.35 by 490 by 979 gives a Q equal to 6.48 times 10 to the 5 joules. This can also be written as 648 kilojoules. Now let's look at the units quickly. Our kilograms cancel with our kilograms, and we have Kelvin on the bottom and degrees Celsius on top. And in this case, these can be canceled because remember here we did a difference of temperatures. And if we would have converted these to Kelvin, we would have just added 273.15 to both of these values. So when we subtracted and found the difference, we would have still found the same difference. So that's why in this case we can cancel our degrees Kelvin and our degrees Celsius, giving our final answer for part B. If the carbon steel was originally at 19 degrees Celsius, how much energy was added to get it to 998 degrees Celsius? We had to add 648 kilojoules. And now we're ready for part C. In part C, we're asked if none of the water vaporizes, which means it doesn't undergo a phase change and all of the water remains liquid water when the sword is dunked in the water, what would be the final equilibrium temperature of the water and the sword after cooling the sword? Most people, when solving this question, would say the energy lost by the sword would have to equal the energy gained by the water. Now, this is really just conservation of energy. What we're saying is delta Q of the sword plus delta Q of the water must equal 0. Or the change in energy of the sword plus the change in energy of the water is equal to 0. In our case, this would be a decrease in the energy of the sword plus an increase in the energy of the water. To make these equal to each other, we can subtract one of them from this side. So if we subtract the delta Q of the sword from both sides, then on this side, delta Q sword minus delta Q sword cancels out, and we're left with delta Q of water is equal to negative delta Q of sword. You should note, though, that the temperature final of both the sword and the water are equal. So let's write this here so we don't forget. Temperature final of the sword is equal to temperature final of the water, and we'll just call it TF, temperature final, in this question. And this quantity TF is what we're looking for. Now looking at our formula sheet, the formula we're going to use is Q is equal to mc delta T. So for the water, we have the mass of the water multiplied by the specific heat capacity of the water multiplied by the change in temperature of the water. And this is equal to the negative delta Q of the sword, which is the mass of the sword multiplied by the specific heat capacity of the sword multiplied by the change in temperature of the sword. And now substituting in for our change in temperature, we have the mass of the water multiplied by the specific heat capacity of the water multiplied by temperature final minus temperature initial of the water. Now, we don't need to put a subscript on temperature final because, as we discussed up here, the temperature final of the sword and the water are the same, so we'll just call them TF for temperature final. And this is equal to the negative mass of the sword multiplied by the specific heat capacity of the sword multiplied by the temperature final of the sword, subtract the temperature initial of the sword. Since we're going to need a little bit of room for algebra, let's move this equation to the top so we have a little bit more room before we substitute our numbers. So substituting our values into this equation, we have the mass of the water, which is 19 kilograms, and this is multiplied by the specific heat capacity of the water, which is 4,180 joules per kilogram Kelvin, multiplied by the temperature final, which is what we're looking for, subtract the temperature initial of the water, which is 21 degrees Celsius, and this is equal to the negative mass of the sword, which is 1.35 kilograms, multiplied by the specific heat capacity of carbon steel, what the sword is made out of, and that's 490 joules per kilogram Kelvin. And this is multiplied by our temperature final of the sword, what we're looking for, subtract the temperature initial of the sword, which was 998 degrees Celsius. We start to work through some of these multiplications and we keep all the decimal points to avoid any rounding errors. We have 19 multiplied by 4,180, and this gives us 79,420 joules per Kelvin because our kilograms cancel out, and this is multiplied by our temperature final minus 21.0 degrees Celsius and equal to negative 1.35 times 490, which is negative 661.5 joules per Kelvin. Again, our kilograms cancel out. And this is multiplied by our temperature final, subtract 998 degrees Celsius. Now distributing into the brackets, we get 79,420 joules per Kelvin TF minus 79,420 multiplied by negative 21, which is negative 1,667,820 joules. And this is equal to our negative 661.5 multiplied by TF, so negative 661.5 joules per Kelvin. Temperature final, our negative 661.5 multiplied by our negative 998, which is equal to positive 660,177 joules. As we've done before, because we're calculating a difference in temperature here, we can cancel out our Kelvin and our Celsius, because if we were to convert these to Kelvin, we'd just be adding 273.15 and the difference would still be the same. So we can cancel out our units of Celsius on top and Kelvin on the bottom for both of these multiplications, and leaving us with just joules. Now to collect our like terms and get them on the side, we add 661.5 joules per Kelvin to both sides of the equation. And we also add 1,667,820 joules to both sides of the equation. So our negative 1,667,820 cancels with our positive, and our negative 661.5 cancels with our positive, and 79,420 plus 661.5 gives us 80,082 joules per Kelvin multiplied by TF. Sorry, I forgot there's TFs here when we add on both sides. And on this side, so this is equal to 660,177 joules plus 1,667,820 joules, which is equal to 2,327,997 joules. So our 80,082 is multiplying our TF. So to get our TF all alone, we divide both sides by 80,082 joules per Kelvin. So on this side, 80,082 divided by 80,082 just leaves us with our TF. And on this side, 2,327,997 divided by 80,082 gives us a final temperature of 29.1 degrees Celsius. Because our joules cancel out, and although we have Kelvin here, because we did the whole question in Celsius, our final answer actually comes out in Celsius. We could have converted this value to Kelvin by adding 273.15 as well as our temperature over here, and then our final temperature would have came out in degrees Kelvin. One thing to note with the specific heat capacity of different things is that the units are joules per kilogram degree Kelvin. And because 1 degree Kelvin is equal to the equivalent of 1 degree Celsius, because they go up by the same amount, you could do a unit conversion here, multiplying this by Kelvin over Celsius, where the Kelvins cancel. And so we could have given all our specific heat capacities in this question in joules per kilogram Celsius as well. And if you're searching online, Most places give them in joules per kilogram Kelvin, but some also give them in joules per kilogram Celsius. However, the actual value stays the same. So if we gave this in degrees Celsius, it would be 4,182 joules per kilogram degrees Celsius. And then our units would have worked out at the end. As long as you understand how the units are working out, that's all that matters. So if none of the water vaporizes when the sword is dunked into the water, what would be the final equilibrium temperature of the water and the sword after cooling? And this would be 29.1 degrees Celsius. Now, there was a lot of algebra here with big numbers, so you can actually take this number and plug it back in, and then see that these two sides are equal to each other except for the negative sign. And this would essentially confirm your answer. Thank you for watching this video on thermodynamics, where we looked at how to convert from degrees Celsius to degrees Kelvin. We looked at how much heat energy it would take to heat a sword from 19 degrees Celsius to a forging temperature of 998 degrees Celsius. And we found the final equilibrium temperature of a sword and a water bath if we dunked a 998 degrees Celsius sword into a 21 degrees Celsius water bath.